Heat is everywhere, in your phone, in rockets soaring through space, and even in the hidden depths of Mars. But not all materials handle heat in the same way. Crystals, with their perfectly ordered atoms, let heat flow in one predictable rhythm. Glasses, in contrast, have a messy, disordered atomic arrangement, making heat behave quite differently. This difference isn't just academic curiosity. It shapes the electronics in your hand, the shields protecting spacecraft, and the systems that recover wasted industrial heat. At Columbia Engineering, Michele Simoncelli is on a mission to understand this from the ground up, or as Aristotle would say, from the first basis from which a thing is known. His tools: the deep equations of quantum mechanics and the sharp edge of machine learning. Then came a mystery, a material that seemed to break the usual rules. Part crystal, part glass, it behaved like neither. And both. In July 2025, Simoncelli, together with Nicola Marzari and Francesco Mauri, predicted its existence. Soon after, experimentalists in Paris confirmed it. The twist: this rare material had first been found in meteorites. And even on Mars. Its strange heat-handling abilities could inspire new materials that survive extreme temperatures, and even whisper secrets about a planet's thermal past. Back in 2019, Simoncelli and his colleagues had crafted a single equation, one that explained why crystals lose conductivity with heat while glasses gain it. It also revealed how imperfect materials in between behave, such as those used in thermoelectrics, solar cells, and heat shields. When they applied the equation to silicon dioxide, the stuff of common sand, something unusual appeared. A rare form, tridymite, described in meteorites decades ago, should have a thermal conductivity that barely changes at all with temperature. To test this, researchers gained special access to a piece of tridymite from a meteorite that fell in Steinbach, Germany, in 1724. Their measurements matched the prediction exactly. This thermal constancy is so unusual it recalls the century-old Inver effect, which once won a Nobel Prize. Here, the tridymite structure sits perfectly between order and disorder, crystal and glass. Simoncelli's team went further. They predicted the same structure could appear after years of thermal aging inside the bricks of steel-making furnaces. Why does that matter? Because steel production is a giant carbon emitter, nearly 7% of US emissions, and better heat control could help cut that footprint. In his latest work, Simoncelli used AI to overcome the slow grind of traditional physics simulations. With quantum-level precision, he mapped how atoms in hybrid materials guide heat. These same quantum rules might also apply to electrons and magnetic excitations, paving the way for wearable thermoelectrics, neuromorphic chips, and spintronic devices. His group now works on three intertwined goals: build first principles theories that match experiments, develop AI tools to predict material behavior with pinpoint accuracy, and design entirely new materials to meet urgent industrial challenges. And all of it began with a simple question: how does heat really move?